if you start with something like x-axis, y-axis here, and it's simply rotation, so size of the vector doesn't change. So if you just start with this, and if I rotate this, let's say 45 degrees, ideally I should have called my x and y axis as these. But in the interpretation of linear transformations, we were still assuming that this is the x-axis and y-axis. I hope this is not too confusing. If this is confusing, I'll try saying it in some other way. Did you guys do the homework questions where like one of the questions was trying to find out what is the resulting position of a vector when you rotate the overall coordinate system by 45 degrees or by theta degrees or whatever? Was that a homework problem from 4 weeks ago? I don't remember now. Does anyone recollect? Okay, let's go check. Okay, no problem. Yeah, so I think this is really just one small idea. If I rotated this by 45 degrees, where did my unit vector land? It landed somewhere here, right? And it landed somewhere here. But we are still giving the positions of these. Yeah, so I started from here. This is my unit vector along the x-axis, and this is my unit vector along y-axis. I rotated this 45 degrees. I rotated this way, anti-clockwise direction by 45 degrees. Then my initial unit vectors would fall somewhere around along these lines, right? Is that clear? After rotating it, just this is the new position of those unit vectors. Okay. What is the coordinates of this particular point here? Okay, how many of you know trigonometry or have seen trigonometry before in some other context? Okay, so if we take a this is a right angle triangle with hypotenuse of length 1, and this angle is 45 degrees. What is this side and what is this side? Obviously, this is an isosceles right angle triangle, right? Because this is also 45 degrees here. So these two are the same. For those of you who don't know trigonometry, let's assume this is x. Now we get 2x square equal to 1, right? This is Pythagoras theorem. So x equal to 1 over square root of 2. I jumped a few steps here. If it's not clear, I'll go over in more detail. But if this is clear to you guys, we'll just skip these things. So the coordinates of this new point are 1 over square root of 2, comma 1 over square root of 2. But if we had rotated x and y, does it make sense to still say this is 1 over square root of 2? And how did I get square root of 2? Consider this right angle triangle. Could be good if I... One of the angles is 45 degrees, other is 90. Yeah, exactly. Yeah, that's the basic idea. Yeah, cos theta, sin theta, and so on. Yeah. So if you know trigonometry, yes, that's a very straightforward leap from there. But if for those of you who don't know trigonometry, this is just a way to do this one. So if this angle is 45 degrees, what is this angle? This is 45. What is this angle? 45. So this is an isosceles triangle, right? So if this side length is x, this side length is also x. And hypotenuse is of length 1 because this was originally our unit vector. right? Unit vector means it's of length 1. Does that make sense? So now I'm simply applying Pythagoras theorem. So I'm saying x square plus x square is equal to 1 square. So that's 2x square equal to 1. X square is equal to half. X is equal to square root of half, which is 1 over square root of 2. So that's how we got the new place for this particular point. You can go calculate this particular point's position as well. I'll not be doing that right now. You can calculate it. Already you guys would have done it in homework anyways a few weeks ago. But if you notice, this point's coordinates are 1 over square root 2, 1 over square root 2, assuming that the x and y axis are still the horizontal and vertical axis, right? If we assume this is the x and y axis, then this point's coordinates are just 1, 0, right? It's just like you take a graph paper, you rotate it. Did the x-axis and y-axis change because you rotated it? On the graph paper, they haven't changed. But from the angle in which you're seeing, if you're still seeing, looking at it straight downwards, now your relative x and y-axis have changed, right? So that's a small problem if we have to constantly remember, oh, this was my original x-axis, this was my original y-axis, and all coordinates will be in the original coordinate system. That's a unnecessary burden that you have to carry over, right? It may not seem like a burden if you do it in 2 dimensions. Obviously, it's very straightforward. But if as the number of dimensions increase, it's really difficult to keep track of, okay, the coordinates of this point in the original axis are these. So as a way of getting rid of this burden of keeping track of original coordinate axis, eigenvectors were introduced. So just before we go into eigenvectors, what we saw is a matrix represents a linear transformation. This simply is the position of 1, 0 and 0, 1 after doing the transformation. Where did these two vectors land? But these coordinates are in the original coordinate system. So it's not necessarily a good way of representing these. So what people thought of is, okay, how could we do something so that we don't have to keep track of our original axis? And their idea of, actually this is not something that came up automatically, but one idea that came up was, okay, what if there were some lines whose position does not change even after you do the linear transformation? What if there were some vectors whose position does not change? Those are called as eigenvectors. When you take initial x and y axis, these unit vectors that we are drawing are the eigenvectors for all the other things in the plane. So if I draw a vector like this is really just this vector multiplied by whatever. So let's say 5 times unit vector along x direction, and let's say 4 times unit vector along y direction. So this is 5, 4, right? So that's, you've already used eigenvectors, but they were just simply called as coordinate system. So your x-axis and y-axis, these are the eigenvectors for this particular transformation, which is simply writing down like this. So for this matrix, the eigenvectors are just 1, 0, 0, 1. Now, what does an eigenvector really mean? It is a vector whose position doesn't change after the transformation. How do you, if let's say a matrix A represents the linear transformation, how do you find out the final position of a vector X? If you apply this transformation, how can we find out that one? So under this linear transformation A, what is the final position of a vector X? How can you find that? Anybody who wants to volunteer with the answer? So we have a linear transformation A. We want to know what is the final position of vector X. How can you find out this one? How many of you remember or probably don't remember? Just a general transformation. This matrix A represents a general transformation. Under that general transformation, we want to know where the vector X lands. And that's the purpose of this thing called matrix vector multiplication. So the final position of this vector is AX. Right, you guys already did this a few times in homeworks or whatever. You already tried this. Maybe just a refresher. So when you multiply a vector with a matrix, what you get is the final position of that vector. When you perform that transformation. Does this make sense? Anyone for whom this is not clear? Why AX gives you the final position? Okay. So if AX is the final position, if X was an eigenvector, my claim is that its position doesn't change. It only increases or decreases in length. So the way to write this is AX equal to lambda X. This thing represents the final position of vector X. This says that vector X did not change in place. It simply increased or decreased in length. Lambda is a scalar. So what I mean by that is, let's take, for example, actually, let's take some simple matrix. Can you guys tell me a couple of transformations? Let's first do XY. So some transformation. You guys tell me, then we'll calculate a matrix corresponding to that. What transformation would you guys like to do? Don't go for crazy ones because that will waste time. Some simple transformations. Transformation means, okay, scaling along X by a factor of 3. Okay. So scaling along X by a factor of 3. That means this becomes this, right? So our 1, 0 becomes 3, 0. And our 1, 1 still 0, 1 still stays 0, 1. Right. So this is one transformation. So 3, 0, 0, 1. Some other transformation. Does this make sense how I got here? What Shruti said is we just want to stretch it along x-axis, right? You're just stretching. Horizontal translation by 8 units. So what happens if you do horizontal translation by 8 units? This point here would go all the way to this point here, 9, 0, right? So that's another transformation. This point here also would go to 9, 1. Okay, so that's another transformation. Anyone else wants to volunteer and suggest some other transformation? Isn't it 8-1? Yeah, you're right, 8-1. Okay, so 8-1. Any other transformation someone who wants to suggest? Rotate by 90 degrees around origin. Okay, if you rotate by 90 degrees around origin, can someone say what will be the final positions of 1, 0 and 0, 1? So I start from here. This is my vector 1, 0. This is vector 0, 1. Rotate. You mean clockwise or anti-clockwise, Prince? Clockwise. Okay, so if you rotate this clockwise, this goes here and this comes here, right? So I'll try to draw this in a different color maybe. So now what are the new positions of these two vectors? So where did this 1, 0 end up? What is this point? Minus 1, 0. What is the exact? Yeah, 0, minus 1, right? Because the x 1, 0 went to, okay, and this is 1, 0. So this becomes 0, minus 1 and 1, 0. The position of the unit vector along x-axis and the position of unit vector along y-axis after the transformation. Okay, now we have good enough transformations. So what if I applied all three transformations together? What is the resulting matrix? 1001 cos 360 minus sine 360. Why 360? Isn't it simply cos 270? Or if you want to write, it is minus cos 90, right? Cos 360 would be just the complete rotate by 360 degrees. Right, okay. Right, so what Shruti is giving us is the generalized form of rotation by angle theta degrees. So if you take this and rotate it in anti-clockwise by angle theta, that is equivalent to rotating this by cos theta and sine theta. For those of you who know trigonometry, this would make sense. Otherwise, just ignore this. This is minus sine theta cos theta. So this is where the unit vector along x-axis would land, and this is where the unit vector along y-axis would land. If you don't know this notation or trigonometry, just don't worry about it. It's a relatively straightforward idea if you know those concepts. If not, it's just meaningless symbols, and that doesn't take away anything from our current topic of discussion. So what is the resultant matrix if I perform these three operations? So stretch along x-axis by 3 times. So just stretch that paper 3 times along x-axis, and then shift everything by 8 units to the right, horizontally only, and then rotate it by 90 degrees. If I perform these 3 transitions one after the other, what is the resultant matrix corresponding to the entire transformation? How can I find that? Okay, I'll just randomly ask someone. Meghna, how can I find that? If you guys don't answer, I'll just keep asking someone till someone answers. Oh, am I saying something? Yeah, I'm saying something. Can you hear me? Oh, okay. Okay, so my question was, if we perform these three transformations one after the other in sequence, so first this transformation, then this, what is the final resultant transformation? Can I write it as a single matrix or do I have to write it as three matrices?
Well, you could write it as three matrices, but I'm pretty sure you would be able to write it as one.
Right. How can I find out the single matrix representation for this series of transformations?
Wouldn't you have to do it like as though you would do like simultaneous equations? I don't know.
Okay. Someone else, Tanishka.
Yeah.
So how can I find out the resultant matrix for these three transformations together?
I think that you apply one, like you apply the first transformation and then you use that as your like matrix, and then you apply the second transformation and then you take that as your matrix and then apply the third transformation, I think.
Right. Yeah, you're right. That's how you would apply if you were doing manually. But if I want to find out the resultant matrix, how can I have these three transformations. If I want to find out the resultant matrix, can I just, what operation should I perform to get one? I really want just one matrix that represents these three transformations together. What should I do with these three matrices to get that one matrix? Multiply. Okay, I single multiply. Okay. So can someone multiply? Yeah, absolutely. Yeah. Can someone multiply these three matrices and tell me what's the final answer? You can do this using Python. You don't have to do it by hand. For those of you who want to try it by hand, you can try it by hand also. For those of you who are trying this, did you get this one or did I do something wrong? Is someone else trying multiplying these three? I don't know if I got it right or wrong. If someone else has tried, please let me know if I got it right or wrong. Okay. Okay, so let's assume this is right. If it's not right, someone please let me know. So now our goal is to find out which vectors did not change in position after we applied this transformation. So let's see if that is possible. So how do we do that? Basically, what my claim is, I have these 3 minus 27, 327 minus 1, 0, and I have a vector, let's say AB. What I'm saying is this vector's position only position changed. How did you get 327? Matrix multiplication, Vidyut. You can try it on your computer or you can try it on by hand. I multiplied first matrix with second matrix with third matrix. These were the three matrices, right? Okay. So if I take this vector a comma b and multiply with this matrix, my claim is I'll end up getting just the same vector a comma b, but with some scaling and nothing else. That's my claim. So how do I find such a vector? Anyone, any thoughts? How can we find such a vector? Okay, so let's see what we can do to solve this. 3a plus 27b minus a plus 0 is equal to lambda a lambda b. Right, so what does this mean? This means 3a plus 27b equal to lambda a minus a equal to lambda b. So I found out the value of lambda, which is minus a by b, right? But does that satisfy the first equation? Doesn't look like it satisfies the first equation, right? So what can we do to find out better? So let's try something else. Here the coefficient of this lambda a, so let's do this, 327 minus 10 ab. When I say multiplied by lambda, what I really mean is multiplied by a vector like this. Because it doesn't make sense to really just multiply randomly, but I'm multiplying by this matrix lambda 0 and 0 lambda. So if I transpose this, what I get is 327 minus 10. If I transfer this to the other side, I get minus lambda 0 lambda times ab equal to 0. All I did is same as some basic math that you do, like ax equal to 4. So that means ax minus 4 equal to 0. Same kind of idea. I just transferred this matrix from right side of the equation to left side. Now this results in 3 minus lambda 27 minus 1 minus lambda. Can you divide by matrix with a and b? So division is not really available. For matrices, division is equivalent to inverse of the matrix. I could divide it, but what will I get? I really wanted to get all the a and b's to one side, right? Like my ab is like my variable here. So ax equal to 4x is my equation. What I want to do is bring all the coefficients of the variable x or this vector AB to one side, right? That's the goal. If I divide by matrix with AB on both sides, it will just not cancel out because AB is not a matrix, right? AB is a vector. It does not really represent anything other than the position of a line. Dividing by the position of a line doesn't really make sense, right? Okay. So now that we have this is where I'm going to jump a little bit because we are already little short of time in today's class. So the way to do this is by claiming that the only way this becomes 0, 0 is if the determinant of this particular matrix is 0. You guys can Google and learn how to calculate determinant of a matrix. It's relatively straightforward for a two-dimensional matrix like this. It's simply multiply these two, and subtract them. So we get 3 minus lambda times minus lambda minus or plus 27 equal to 0. So only when the determinant of this matrix is 0, then we get a 0 vector. That's a claim, and I'll send out some notes on why that is, if you are interested in learning why it is so. So what does this become? We get minus 3 lambda plus lambda square plus 27 equal to 0. For those of you who know how to solve quadratic equations, what is the solution for this one? What are the values of lambda? Anyone? So if lambda square minus 3 lambda plus 27 equal to 0, what's lambda? Okay, I'll just randomly ask few people. Okay. Rohan? Imaginary, yes, good. Yeah, it's imaginary. What is that imaginary number? Oh yeah, of course. I is that imaginary number, but right. Is it 9 plus? It is 9 minus, right? Right, exactly. Yeah. Yeah. So Shruti's answer is matching my answer. So it's 3 over 2 plus whatever. So when you see an imaginary number like this, it's little hard to visualize because we have a real axis here. We had x and y's, all of them are real numbers, and we are saying the only eigenvalue is an imaginary one. That doesn't really make that much sense. And there are two values here, right? So two values of lambda. For each value of lambda, we get one value of the vector a and b. So this is a transformation which doesn't have any real eigenvectors. Actually, who can tell me why is we did three transformations, right? Stretching, pushing, rotating. Once you rotate your graph paper, is there any line on the graph paper whose position has not changed once you rotate it? Right, and that's exactly starting point, but I was talking about line, right? Like, is there any line whose position doesn't change? Right. Yeah, because vector represents the line, and eigenvector represents any line whose position does not change after doing the transformation. But if you do a rotation, there is no line whose position does not change. But we still got an imaginary number. Now, this is beyond what I can explain in today's call, but you can still really visualize some vector whose position hasn't changed. Yes, absolutely. This will be much more easier if you do this physically on a graph paper, of course. But let's do this numerically on our screens, and then we'll go to graph papers. Maybe as part of your homework, you guys can do something on graph paper. I'll think of some problem where you can do it. Complex plane, yeah, it's a complex plane, but again, that's not really what I wanted to go over today. So let's try a simpler example. Let me Google and find some example where we'll find a decent eigenvalue so that I can show you what it means. I'll find like some linear transformation for which there is a okay. So we want to find out what are the eigenvalues for this particular transformation. It's an odd looking transformation, but let's see what are the eigenvalues for this or eigenvectors for this. So how do you do that? We're trying to find out what are the eigenvectors for this or eigenvalues first. What does that mean? Those are the, okay, what does that mean? What does eigenvector mean? So eigenvector means eigenvector is a vector whose position does not change. Just the size of that vector increases or decreases when you do this transformation. Right. Yeah, perfect. So we have this transformation -2, 12, 1 minus 3. If you take a vector AB, the result of this is this vector AB. Right. So how do we do this?
Mom, how are you?
Someone is asking something.
Yeah.
Do you have it?
So I'll do that. Okay, thank you. Okay.
What is the -6 in the matrix? You mean this -2 here? Or this minus lambda here? Right, the lambda, okay. What is that? That's just a scaling factor. So you can do it anyway. So by definition, an eigenvector is something whose position doesn't change, right? So if I am at a position A comma B, the final position of this new vector also should be A comma B, but it could be increased or decreased in length by something. So I don't know what is the increase or decrease in length, so I'm calling it lambda. So it's
Okay.
assuming something like, sorry, does someone have a question?
It's just a variable?
It's just a variable, yeah.
Okay.
You can
Yeah.
call it x if you want. Where is lambda from? It's a Greek letter, yeah. Oh, you're confused with the letter. Okay, well, I'll just stick to letters that you're commonly aware of, x. Okay. So what this means is somehow some crazy transformation, there is this vector here whose position doesn't move in some transformation, but its size might change. Instead of being a and b, well, it's probably this is a, this is b. Instead of being a b, its position is maybe like x times a and x times b. So that's the idea. So the vector ab's position has not changed, but it has increased in length or decreased in length. Its direction is the same. So now I go and take this to the left side. We get minus 2 minus x, 1, 12 and minus 3 minus x times AB equal to 0, 0, right? This is like your basic linear algebra with just matrices. So just a few minutes ago, I told you how to calculate the determinant of a matrix. It's multiplying these two and then subtracting the product of these two. So if you multiply minus 2 minus x times minus 3 minus x and subtract 12 times 112, can you simplify and solve this equation? Can someone simplify and solve this equation? I'll wait for you guys. I'm waiting for you guys to solve this. Prince, can you check once? Is that correct? Right. So Shruti, yeah, Prince, you just got signs opposite, like minus 6 and 1, right? Yeah. One and minus 6. Perfect. So we got two values of x, 1 comma minus 6. What this tells us is there is one vector, there are two vectors whose position hasn't changed. For one of them, the length also hasn't changed because its scaling factor is just 1. So there is one vector whose position and length haven't changed. Then there is another vector whose length has changed, but its direction is the same. Its length has increased by 6 times and it got rotated by 180 degrees. That's what this represents. So for this transformation, when this transformation happens, there are two such vectors on the graph paper whose directions or whose positions haven't really changed, but lengths have changed a little bit. What are the vectors? We'll have to find out what are those vectors right now. So let's substitute each value. So the first one is 1, right? So what we are saying is minus 2, 12, 1 minus 3 times AB is equal to 1001 times AB. right? So actually, we can even substitute in this one itself. We don't have to substitute there. Let's substitute there. So we get minus 3, 1, 12, minus 4 times AB equal to 0, 0, right? We're substituting this value of x back into this equation. And we are trying to find out what are these AB. So we get two equations, right? This is minus 3a plus b equal to 0 and 12a minus 4b equal to 0. If we solve these two equations, what do we get? Is that because the position doesn't change? Is what, Meda, can you ask your question instead of typing?
Oh no, I was just saying for the first one that you wrote, that the 1 over the 0, 0, 1 times the AB equals the negative 2 over 12, and then 1, negative 3, like that all equals
Like
each
this
other.
one? Like yes, because for one value of x, which is 1, the position of this vector is only changing by a unit length.
Okay, yeah, thank you.
Okay, good. Right. So obviously, after you have solved this, a equal to 1, 3. Right. So a equal to 1 and b x and 3x. Right. So someone already got it. X and 3x. So basically, what this is these two equations really just represent the same thing, right? If you look at this equation and divide it by minus 4, you really just get minus 3a plus b equal to 0. Right. These are just same equation given twice. Right, these two equations are exactly the same thing. So how do you solve this? Basically, it's minus 3a equal to minus b. So b equal to 3a is the equation. So the vector whose position did not change is the vector where you can take any b, so it doesn't change, right? So a and 3a. So any vector of this form, so whether it is 1, 3 or 2, 6 or 3, 9, whatever, all of these vectors are in the same direction, because that's what this really represents, right? When x is 1, y is 3, that's this point. When x is 2, y is 6, that's, let's say, this point. So this vector in this direction does not change under this transformation, minus 2, 12, 1, minus 3. So that's our first vector whose position nor size changes. Does this make sense? Okay. Now let's look for the second vector. So we have minus 2 plus 6, that's 4, and 1, 12 and 3. So 4, 1, 12, 3. Again, it's the same thing. We got two vectors, two rows, which are really identical, because if you divide the second row by, no, let me write it properly so that you guys don't. So minus 2x and 1. So this is our transformation. When I substitute x equal to minus 6, what do I get? I get 4, 1, 12, 3. If I substitute x equal to minus 6, this is what I get. Obviously, you guys can notice that the first row and second row are really the same. The second row is just 3 times the first row, right? So again, it's the same kind of thing. 4a plus b equal to 0. So b equal to minus 4a. So this vector is in the direction a and minus 4a. So if I substitute different values of a, I get this. So what is this vector in this coordinate axis? For 1, it is minus 4. For 2, it's minus 8. So it's something along this direction. So a vector along this direction got rotated and increased by 6 times in the opposite direction after that transformation. A vector along this direction did not even change anywhere. Okay, I'll pause for a second. For those of you who did not follow, please let me know. We can try out a few more examples if you did not follow the steps so far or the intuition so far. Please don't feel shy to say if you did not follow, because in today's class, I'm really trying to, in today's session, I'm trying to go over a broad range of topics, and this is just the beginning. So if you don't understand this.
Can you do another example?
Absolutely, yeah. So let's do another example so that we can at least numerically understand what is happening. Let me find another matrix that. Problem is, I don't want to give you like a matrix that is that gives a imaginary solution. Okay, so let's try this one. 1, 4, 2, 3. This time I would like for you guys to try it along with me. So what is our goal? Satvik, what is the goal? What are we trying to find out?
You're trying to multiple scale this. You're trying to get another matrix so that I don't really know.
No problem. Let me repeat. So we are trying to find out vectors A, B. So this represents a vector. If I just write numbers in a column, it represents a vector. So vector is just lines. We are trying to find out lines on the graph paper whose direction does not change after doing the transformation. So that's our goal. We are trying to find out such vectors. When I say direction does not change, its size could change, which is okay. Yes, the line does not rotate. It's in the same direction. So if you took a rule, it can get shorter or longer. Absolutely, yeah. So when I multiply by this x0 and 0x, if you notice, what does x0 and 0x represent? It simply represents, so if I had a unit vector 1, 0 like this, and if I stretch this graph paper uniformly, this is just x0 and 0x, right? So it's a scaled vector, or it's a vector whose size has changed but direction is the same. So that's our goal, because that's the definition of an eigenvector. So it's the same vector, but size has increased or decreased, but it's in the same direction. So to find this, I have this matrix now, Ax equal to lambda x. I'm saying this is equal to A minus lambda times x equal to 0. This seems normal, right? Like you guys don't have any, is this clear, like what I did here? Okay, so this is my matrix A. So this is my matrix A. This is my vector x. This is my matrix lambda. This is my vector x again. So this matrix equation can be written as this more algebraic looking equation of Ax equal to lambda x. Is this clear now? So I'm just writing symbols instead of A. Yes, A is the transformation. Yeah, A is this matrix of the transformation. Yeah, I thought we already went over this notation in previous classes, so I'm just skipping some of that. No, it does not mean A equal to lambda, and that's because it's a transformation, right? A is some stretching, pushing, pulling. Lambda is what happened to just that one vector, right? Just this one special vector got scaled. All the other vectors got rotated, got pushed somewhere, pulled somewhere, and so on. So A is not equal to lambda. Okay. So what do? I'm now saying this is equivalent to A minus lambda times x equal to 0. Is it clear why A is not equal to lambda to everyone? Okay. Does anyone else have that same question, like why A is equal to lambda or A is not equal to lambda?
Could you explain it again?
Right. So A represents, so let's try drawing something. Let me see if I can draw that well. I'm not sure that if I can draw that well. So let's say this is a vector on our plane. Somehow, I'm trying to draw this in a way that so I did some transformation. I don't know what transformation, but some sort of pushing, pulling, stretching, whatever. And this is what I ended up with. My initial axis all got shifted, but somehow this one vector stayed in position. All other vectors got moved, but this one stayed. I'll send you guys some videos where you can watch somewhat nicer transformations, because if you see it, you can easily believe it, but logically this is what is happening. Every other vector on the graph paper moved except this one guy. How that happens, I'll send you some video. If I find a good video, I'll send you a good video where they would have drawn this, or they would have turned the paper nicely so that you can see this. But this is what is the meaning of an eigenvector. Why doesn't A equal to lambda? Yeah. So what A represents is what happened to these two vectors, right? That's what A represents. Right? That's, if you remember, A was simply where did this vector land and where did this vector land, right? Meda, is that clear? Right. But this particular vector did not undergo any transformation at all, right? It's still in the same position. or the only transformation it underwent is a scaling by lambda. It only got increased or decreased in length. It only got increased or decreased in length, but did not move. If I assume A equal to lambda, then these two vectors also shouldn't have moved. So that's why A is not equal to lambda. Because lambda is the transformation that's happening to this one special vector, whereas A is the transformation that's happening to all the vectors. It's not a transformation really. There is no lambda transformation happening. When I apply the same transformation A to this vector, the result is simply that this vector just scales and does not move. That's the result. That's why A is not equal to lambda. So now we have this matrix here, 1, 2, 3, 4. So we have a vector A. And this is the result of the explanation that I just gave. Applying this transformation A on this vector A, vector AB, results in just a scaled copy of the same vector. Now, how do we solve this? If you are doing it in class, you would do 1, 2, or if you are doing a equation with normal variables that you are familiar with, you would do something like this. Right? This is the coefficient of this vector. This is the coefficient of this vector. I'm collecting the coefficients together. Something like this, 4x equal to, let's say 12x, or no. Yeah, something like this, 4x plus 3 equal to 12x. So you would do something like this, right? 3 equal to 12x minus 4x. I did the same thing. I'm taking a, b as my variable x and just subtracting the coefficients. Is this clear? If you don't understand this, it is not going to be easy for you to follow. Please don't feel shy to say if you don't understand. Is the bracket represent multiplying? Yeah, this is multiplying. Here you can assume that these are multiplying. So let me try writing this in more smaller way. So this is our starting point. So I'm rewriting this as actually, let me write the intermediate step, maybe that here. So I'm rewriting this first as 1, 2, 3, 4 times AB minus lambda 0, 0 lambda times AB equal to 0, 0. This is one step, right? All I did is took whatever is on the right hand side and brought it to left hand side. Is this clear? Okay. So now I'm trying to use distributive property on this. So I'm trying to say 1, 2, 4, 3. Minus lambda 0, 0 lambda times AB equal to 0. What does matrix? The matrix 1, 2, 4, 3 really means I had this initial vector 0, 1. This vector landed in this position and this vector landed in Let me draw in a different color so that it becomes clear. So somehow after my transformation, this is what happened. So this vector along this direction ended up here, and this vector along this direction ended up here. So some sort of squishing, rotating, twisting, whatever, some transformation that led to this. Does that make sense, Satvik?
Yeah, so basically the 1, 2, 4, 3 matrix is the initial matrix.
No, this is the result of the transformation, right? Like, so this vector 1, 0 ended up at position 1, 4. This vector 0, 1 ended up at position 2, 3.
Oh, so that's like after the transformation, that's what comes up.
Wait, this is just the transformation.
Oh, okay.
This matrix represents what happened to what was the transformation. Okay, so continuing on, at least with the numerical part. So is this equation clear now? So we started with a vector, applying a transformation to a vector. We applied a transformation to a vector. We simply got a scaled copy of that. AB is just a vector, Tanishka. It's like if you were getting confused with AB, we'll just call this XY. It's just a general vector. We don't know what is the position of that. Okay, so we have this generalized equation now. So if I have two matrices like this, I do point by point subtraction. So first position, first value gets first row, first column, subtract first row, first column. So that becomes 1 minus lambda. Sorry, we were starting with, yeah, okay. Then 2 minus 0, then 4 minus 0, then 3 minus lambda. This is matrix subtraction. You guys tried this with array addition or array subtraction previously in Python also. So is this step clear, like how we got from here to here? It's I replaced that with x and y because somebody pointed out what is AB. How is lambda subtracted from 1 and 3? It's this pairwise subtraction. Why is it subtracted? Okay, I have an array here with 1, 2, 3, 4. That's why is it subtracted? That's a good point. Why is it subtracted? Because I'm trying to find out I group the coefficients of my vector xy, and that's the resulting coefficient of the transfer of the vector that I have in this equation. So something like this, 4x plus 3 equal to 2x. What do you do, Satvik? If you get 4x plus 3 equal to 2x, what do you do? A minus ax plus 3b. Okay, let's see. So, okay, first let me answer Satvik's question. So Satvik, what do you do if you have this equation 4x plus 3 equal to 2x? Satvik?
Yeah. So before that, I want to answer a question. Would that mean
So
I would isolate? I would like. I would. I want to ask a question though. Does that in the equation 4x plus 3 equals 2x, would 3 equal to negative 2x?
okay, so how did you get that?
I just subtracted 4x from both sides.
That's all I did. I subtracted lambda 0, 0, lambda xy on both sides. I subtracted this from both sides.
Okay.
For me, this is like 4 and this is like 2. This is still like x. So in this form, if you write it in this form, for me 1, 2, 3, 4 times x is simply like 4x, and lambda 0, 0, lambda times x is like 2x. What do? I have to group these two together on one side, right? Okay, cool. So that's second question. What was your first question? How is lambda subtracted? Yeah, so that's pairwise subtraction. So I have 4 numbers in this matrix, 4 numbers in this matrix. I take the first number in first row, first row value in first column and first row. What is the purpose behind doing this? To calculate the eigenvalue and eigenvector. What is the purpose behind doing this?
Wait, what's the purpose of doing that?
What's the purpose? Why do you do this? 3 equal to minus 2x, x equal to minus 3 by 2. Why do you do this?
Because I want to isolate the x, so it's only on one side, so it'll be easier to solve for x.
So you want to find x. Same reason I want to find this xy. I want to find this xy and lambda. Right? I have two problems here. I don't know what is this lambda and I don't know what is this xy. So I'm going step by step to first find out what is lambda, then use that to find out what is xy.
Your audio just suddenly stopped working a little bit.
Oh, my audio stopped working. Is this? Can you hear me better now?
It's not working very well.
Okay.
Yeah, this is better. This is better.
Yeah, I'm not sure what's happening, but is it clear now?
Yeah, it's clear now.
Okay, so I have two variables here, or two kinds of variables. I have one lambda that I don't know, and I also don't know what's this xy, right?
Yeah.
So the purpose of doing this whole process is first find out what is lambda, then find out what is xy. That's the goal. That's what I am trying to find.
So you have to find lambda to find xy?
Right, that's all right. Like I have to find one of the variables, substitute backwards and find the other variables. That's the same idea in anywhere. Whenever you have multiple variables, you find one variable first, then substitute. You have lesser variables, then you find something. Right, yeah, that's possible. Yeah, Prince, let's solve slowly. So first to find lambda, my claim is the only way this is to find this discriminant. So this is a leap of faith. I'll send you guys some notes. You can read that one. So is this subtraction clear? 1 minus lambda, 2 minus 0, 4 minus 0, and 3 minus lambda.
Yeah, I understand that.
Okay. So now Shruti Satya asked a question. Isn't this going to be something? So let's see what is that something. I have 1x plus 2y. So x plus 2y. And then 4x plus 3y equal to lambda x equal to lambda y. Right? So if I do this, I have x times 1 minus lambda plus 2 times y, 4 times x plus 3 minus lambda times y equal to 0.
How did you get those equations? Like 2y is equal to lambda x. Not those other.
So I multiplied this matrix 1, 2, 3, 4 with xy.
Yes.
So that gives us these two equations.
So, but how? I mean, how does it give it?
Yeah, maybe 4 weeks was too much of a break, but let's try. So 1, 2, 3, 4 times xy, because this is the final destination for this point x. So I have to multiply x with 1 and 4. And this is the final position for the y coordinate. So I get y
Okay.
times 2, 3. So this is x, 4x plus 2y, 3y. So I get x plus 2y, 4x plus 3y. This is matrix vector multiplication.
Oh, I understand that.
Right. Then repeat the same thing with lambda 0, or 0 lambda. So this is
And then you got the
x,
other by that.
this is x times lambda 0.
And then y times 0 lambda.
Right. So this gives us equal to x lambda, y lambda. So now I'm saying this first one is one equation, second one is another equation.
Oh,
Right? So x plus 2y equal to lambda x and 4x plus 3y equal to lambda y. Now I'm grouping all the like terms together. So that's x minus lambda x plus 2y equal to 0 and 4x plus 3y minus lambda y equal to 0. Right?
wait.
So
But
what do we get? X times 1 minus lambda plus 2 times y equal to 0. Then 4x plus 3 minus lambda times y equal to 0.
Why are we grouping the 3 minus lambda y together?
These are the terms with y as the variable.
Oh, okay.
Right. So if I drop the x's and y's, I get this matrix 1 minus lambda 4, 2 and 3 minus lambda. Right? So Shruti, looks like it's the same thing, right? So you used x's and y's. I'm just dropping the a's and b's. In your example, I'm dropping the a's and b's. I would just get 1 minus lambda, 1 minus x and 3. Right. No, that's okay, but it's the same matrix. So what we are claiming is we'll calculate what is called the determinant of this matrix, which is multiplying these two values. So 1 minus lambda times 3 minus lambda. And then subtracting the product of the remaining two values. So 4 times 2, 8. And equating it to 0. So by solving this equation, I'll get the value of lambda. So can someone solve and message the values? This is a quadratic equation, right? Can you solve this quadratic equation and find out what are the value of lambdas? Please message me privately so that others don't see your answers. Whoever else is trying can also try. After you solve this, we can take a quick break. Okay. 2 of you messaged so far. Is anyone else trying? And both of you sent me different answers. So I want to see if a third person sends me a better answer. How did you get the new matrix? You mean this matrix, Shruti? Right. So same process, right? I started from this this set of equations, which is what you had also done, right? Starting from this represents a set of two linear equations in two variables. This represents a set of two linear equations in two variables, right? So this is my left hand side, this is my right hand side of that equation. Is this clear, Shruti? Is this part clear? Okay. Then I simply said this first value should be equal to this first value, and the second value should be equal to the second value. That gives me a set of two equations. Then I grouped all the terms on the left hand side. So I had x lambda x, so that becomes x minus lambda x plus 2y. And then I had 4x and 3 minus lambda y. Is this part clear? So then I just drop the x's and y's. So I get this new matrix. Okay. So lambda minus 1 times lambda minus 3 minus 8 equal to 0. Can someone solve this quadratic equation? So far, two people messaged me the answer and their answers are not matching. Can someone who knows quadratic equations try solving these? Okay, you can think of this as x. If that makes it easy for you to solve. X minus 1 times x minus 3 equal to, okay, still, okay, so at least 3 people's answers matched, 4 people's answers matched. X square minus 4x plus 3 minus 8 also, right, Meghna? There is a minus 8. So you get x square minus 4x minus 5 equal to 0. So this is x minus 5 times x plus 1.
How do you solve those equations?
Didn't you do like cross
Oh.
multiplication?
Yeah. If you have not seen quadratic equations before, that's a long shot from here. You might want to Google and find, like, go to Khan Academy or something and see how to solve quadratic equations, because that's a decent amount of explanation that we don't have time to cover right now.
Oh, okay.
Yeah, I can go up to previous page. Oh, I didn't say somebody got it wrong. I just said two people sent me two answers and those answers were not matching. Okay, so what do we get? 5 and minus 1, as several people already replied. So these are the two eigenvalues. Right. Yeah. No, I'm not saying, I didn't say someone, like some two people sent it to me initially or 3 people sent it to me initially and 2 people's answers didn't match. Who sent, I don't remember, but their answers didn't match. So whoever got 5 and minus 1, all of you are right. Whoever did not get that and send it to me, you guys made a basic mistake. I think you did it this way, x plus 5 and x minus 1. because someone sent me this answer, -1, -5 and 1. Whoever sent me that was the one who sent it wrong. Others are all right. So these are two eigenvalues. Now, if I substitute this 5 here, I get 1 minus 5, 2, 4, and 3 minus 5. Right, that's my, I'm substituting this value of 5 here. I get 1 minus 5, 2, and so on. So this is -4, 2, and 4 minus 2. As you can already see, these two equations are the same, right? Like this is just multiplying by -1. If you multiply this by -1, you get the first one, right? Could you explain from how you got the quadratic equation? So you mean this? Right. So the only way, okay, let's see. So I have this matrix here, right? 1 minus lambda, 2, 4, and 3 minus lambda. I'm multiplying this with a point xy, and that's ending up at the origin, right? 0, 0 is the origin, right? So I'm taking a vector, some vector like this. I'm taking some vector like this, applying some random transformation, and you can imagine I'm like just collapsing that vector to this unit, to this origin. That's what's happening in this equation, right? So I'm doing some transformation which is collapsing this vector to the origin. Is this, that seems fine? Does that interpretation look fine to you guys?
Can you explain how you got the 5 and -1 from the quadratic equation?
Right, yeah, I'm going there. If I take any vector and if I shrink it to a point, that's a very drastic transformation, right? I took a line and I crushed it to a point. The only way that a line gets crushed to a point is if basically any transformation is changing this line, right? Like it's taking this line and increasing its length or decreasing its length. If I'm crushing everything to a single point, I'm not just crushing this one line, right? I'm crushing all the points on this line to that one single point. When such a transformation happens, the discriminant of this matrix, and I'll send you guys some videos about what is, sorry, the determinant of this matrix. I'll send you some explanation about what is a determinant. The determinant of this matrix is supposed to be 0. Determinant of a matrix really represents how the area of this changed. So what is the determinant? In here, in this diagram that I drew, can you see this diagram here with these yellow circles now? How did I get the matrix? That is the matrix, right? Yeah, did you get that matrix? 1 minus x, 2, 4, 3 minus x. Yes, I got that matrix. I got 1 minus x, 2, 4, 3 minus x. So I got that matrix, right? Okay. I see where the confusion is. Some of you people are getting confused with the Greek letters lambda. So as you got confused, I was swapping lambda with x, x with lambda, a with x, b with y. That's where all this confusion is. If you guys started with one set of variables, a's and b's, x's and y's, you continue with that. If you started with lambdas, x's and y's, you continue with that. Don't keep swapping in between. I kept swapping because I was explaining to people. But if you are doing it on your pen and paper way, Don't keep swapping as I keep swapping. So this is my starting point. I'll just stick to one set of variables so that it's continuously clear. I have 1, 2, 3, 4. I have xy is equal to lambda 0, 0, lambda xy. Now, same thing for Shruti Satya was 1, 2, 3, 4 AB equal to x0, 0x AB. I changed this xy to AB and this lambda to x. I was operating with two sets of variables. Depending on which pair of variables equations you started with, continue with that direction. Don't switch in between. If you do this or this, you'll get exactly the same answer because the letters don't matter. As long as you don't change the letters in between these two things, it doesn't matter. You start with this and continue with this, or start with this and continue with this. If I continue with this one, I get 1 minus x, 2, 4, 3 minus x times AB equal to 0, 0. If I continue with the first one, from here, I get 1 minus lambda, 2, 4, 3 minus lambda times xy equal to 0, 0. Is that clear now? Shruti Satya, is this clear? Why did the xy disappear? What xy disappeared? Okay, so let's stick with xy's. If this is my starting equation, let's forget AB's, this is my starting equation. Is this okay? Are you fine with this part at least, Shruti? Okay, so now, are you satisfied with this part here? Okay, so far you're good with this. Now, if I take a vector xy, so this is where I was explaining from here, what does a linear transformation really represent? You take these vectors and change their positions, right? This is my final position of this transformation. I took 0, 1, 1, 0 and I ended up at 1, 4 and 2, 3, right? When I do this kind of a transformation, I can get, what I'm doing is I'm taking this square here or this rectangle, this square here, and I'm converting this into this parallelogram here. Does that make sense? But in this particular equation here, I'm taking this point xy and I'm somehow bringing it to 0, 0. So I'm taking a square and making it a point. Does that make sense? Right. So, or rectangle, maybe I'm taking a rectangle. Is the 0, 0 where it shrunk to? Yes, this 0, 0 is where it shrunk to. The only way that can happen is if this matrix behaves in a special manner. That special manner is when this 1 minus lambda times 3 minus lambda minus 2 times 4 is equal to 0. That's the special manner in which it has to behave for this to happen. And I'll send you guys some notes about why this is so. It takes longer to explain that. But if this condition is satisfied, only then you can take a square and crush it to a point. This is some magic. So wait for the lecture notes to see why this magic happens. But believe me on that one for now. So if this special condition is satisfied, then this kind of shrinking or crushing can happen. Is that leap of faith? Can you take that leap of faith with me now, and then we'll figure it out later? Is that okay? Okay. So now we solve this equation. We get lambda equal to 5 and minus 1. When I substitute lambda equal to 5 in the above equation, I get minus 4, 2 and 4 minus 2. These two are really the same rows, right? Because the second row is simply first row times minus 1. Minus 4 became plus 4, 2 became minus 2. Now this times xy equal to 0. So what does that mean? Minus 4x plus 2y equal to 0, or 4x minus 2y equal to 0. Take any one of those equations, you'll get 2x equal to y, right? So our vector xy is really of the form x to x, or just 1, 2 in this direction. So under this crazy looking transformation, the point that was here on 1, 2, somewhere over here, this arrow, let me redraw this here. I'll draw with different colors. Hopefully it is here. So this initial vector 0, 1, 0. And this vector 0, 1. After the transformation went to 1, 4. This is 1, let's assume this is 4. And 2, 3. And somehow this one vector here, which was at 1, 2. So this is 1, this is 2. Somehow this vector at 1, 2. So this is 1, 4. Let's say this is 1, 2. Stayed at the same position. Well, actually got multiplied by 5 times. It's in the same direction, but got multiplied by 5 times because that was the eigenvector corresponding to it, right? Yeah, it's x minus 2. What is x minus 2x? Well, yeah, it's x minus 2y or 2x minus y. So this particular vector got multiplied by 5 times because the value was 5, right? So the vector 1, 2 got multiplied by 5 times. So somehow 1, 2 getting multiplied by 5 times would go to 5, 10. So that's 5 is somewhere here, let's say, and 10 is somewhere here. So this is where it ended up being. So this vector did not change in direction, just became longer. All other vectors probably moved in positions and lengths. Does this make sense? So now let's try with the second value, which is minus 1. So if I substitute minus 1 in this, I get 2, 2, 4, 4, right? So if substitute minus 1 in place of lambda, what do you get if I substitute minus 1 here for instead in the place of lambda? I get 2, 2, 4, 4. Right, when I say minus 1, lambda equal to minus 1, it will become 1 plus 1 and 3 plus 1. So I get 2, 2, 4, 4. That is simply equal to x plus y equal to 0, right? So if it is 2x plus 2y equal to 0, so x plus y equal to 0 or x equal to minus y. Do you guys follow, or do you want me to go step by step? Okay, so I'm assuming you guys followed. So it's just 1 minus 1. So this special vector 1 minus 1 only got multiplied by minus 1. So where would 1 minus 1 be initially on this plane? If this is 1, this is minus 1. So this vector 1 minus 1, if you multiply this with minus 1, what happens? The point 1 minus 1 becomes what? Where does the point 1 minus 1 land if you rotate your axis by 180 degrees? Or where does the mirror image of this lie? Okay, minus 1, 1. Right. Right, because we are multiplying both the points with minus 1, right? When I say multiply this with minus 1, we're multiplying both of them with minus 1. So this point 1 minus 1 becomes minus 1, which is somewhere here. Right. So I'll just draw it in this direction. So this vector got rotated and is of the same length. This vector got scaled 5 times. This got scaled minus 1 times. So this is what eigenvectors really represent. They are the vectors whose position does not, or whose direction does not change. When I say direction does not change, you can get mirror images, that is fine, because they're still along the same line, right? Like I can draw this line, I can extend this line like this in negative direction also, right? So they didn't change. It's still on the same line. Does this make sense?
Yes.
Okay, so let's take a break for 10 minutes. If anyone has questions, we can go over that. After the break, I will go over some applications of this eigenvectors. So 10-minute break. Yeah, 11:30. Okay, be back at 11:30. If you guys are looking at my phone screen and seeing 11:50, that's because I'm in India right now. It's almost midnight for me. If anyone has any questions, you guys can go ahead and ask. Okay, then I'll also take a short break. I'll go some water. Okay, so let's try a quick recap. You guys can answer. You can speak out an answer. You don't have to type because it will waste a lot of time. So a recap of what we did in the 2 classes ago and in this class. What do matrices represent? Anyone, whoever wants to say, you can say. What do matrices represent?
Matrices represent the transformation, linear transformation.
Okay, perfect. What do the columns in a matrix represent?
The x and y coordinates.
Of what?
Of each vector.
Okay, of each unit vector. So if you have a 2 by 2 matrix, the first column represents where the vector along x-axis landed, and the second column represents where the vector along y-axis landed. What does a matrix vector multiplication represent? So if I take a matrix, it represents what is the transformation that happened. So if I multiply that matrix to a vector, what does that represent?
Linear transformation of scaling.
Right, or applying the transformation, not just scaling, right? Like applying the transformation. So when I'm multiplying a matrix, how many of you know this notation? How many of you know what this represents? Function, okay, yeah. So when I do this, right, when I multiply, you can assume this is like f of x is equal to 1, 2, 3, 4. So another way of writing this is f of 2, 4 is equal to 1, 2, 3, 4 times 2, 4. Yeah, in two variables ratio it's y equal to x minus 3. In one, here it's not two variables anymore, right? Like it's more than just a one linear equation. It's two sets of linear equations. So don't replace this with y always. Of course, in general, that is what this represents. But what if I had this? This is the equation for distance of a point from origin in three-dimensional plane, right? So this is not basically saying anything else. This is just a function and this represents something. So don't replace that with y. But this is, when I say matrix multiplication, you can think of it like this. This is a vector 2, 4. Matrix multiplication is simply like multiplying these two things. So it's like applying that function or finding out where this point ends up being after applying this transformation. So matrix vector multiplication represents or gives you where this point ends up, or represents applying this transformation onto that vector. What does matrix multiplication represent? When you multiply two matrices, what does it really mean? Apply two transformations, right? Two transformations, one after the other. So if you apply the two transformations one after the other, then you are applying multiplying two matrices. That's what it represents. And what are eigenvectors? Eigenvectors are vectors whose what is special about eigenvectors?
Direction doesn't change after the transformation.
Right, only scaling happens. Right, so this is the 5 things that we studied in the last 2 sessions. Based on some reaction in this class, I would like to emphasize a little bit. For any concept we'll study in this class or in future sessions, there are few different kinds of things you have to understand. The first thing that I'm trying to see or trying to emphasize is the intuition behind an idea. So when I say matrix, I don't want you guys just to simply think of it as like 4 numbers. My whole focus is on trying to see this interpretation, or what does it represent? It represents a linear transformation, and the columns represent where the unit vectors end up being. And when you multiply a matrix with a vector, that means you're applying the transformation and finding out where that vector lands after applying the transformation. This is all intuition, right? This is not this is not just math, this is intuition. Then there is the mathematical background behind that. We'll try to cover as much as possible on this, but the focus of this session is not really math, because even like in a regular college setting, just doing matrices and as linear transformations and learning about determinants, inverse of a matrix, and trying to find out eigenvectors is anywhere between 4 to 6 or maybe 8 classes, in depending on which kind of college program we are doing. And this is after you guys have finished another 3 more or 4 more years of schooling and maybe 1 more year of college, right? So in 3-4 years from now, you would be spending 4 to 6 classes doing this. So it's kind of hard to go over the math and do very well, but the intuition is actually possible to convey without the math. The next thing is the programming aspect of all the concepts we will study. We want to really program. So my focus is to just concentrate on these 2 things without concentrating too much on this. Of course, sometimes it's unavoidable to do this, but if you are not able to follow the math, try to at least follow the intuition and the programming behind it. If you're not able to follow the math, that's okay. You will study this later in your careers. But intuition, it's better to at least remember what this means, right? Long after you have forgotten English grammar, you'd still be forming sentences. You'll just not be thinking about, is this a subject, object, or whatever other grammar rules you study. You'll still be writing paragraphs, you'll still be writing sentences, you'll be writing more in emails maybe, but you'll be communicating. So that's the same way. That is intuition and programming. So when you write a sentence, you have some sentence syntax, and you know intuitively that some sentences make sense and others don't make sense. Knowing the math is like knowing the grammar. You may not know exactly what grammar rules are being applied, but if you know these 2 things, you will be able to successfully communicate. So that's my idea behind how I'm approaching. So for those of you who are unable to follow the math, it's okay, don't worry about it. But if you're able to follow, great, no big deal. Actually very commendable progress. So now let me show you the programming part of this eigenvectors for today. As always, it's relatively straightforward because somebody else has done the programming for us. So we had this matrix, our transformation matrix A, which was what was it? 1, 2, and if you want to calculate the Yeah, I'll zoom in. Let me first finish typing. I don't know if you can see this clearly, but let's see. So this is what we calculated previously. The eigenvalues are -1 and 5. That's what we had gotten also, right? In our calculation by hand. Did we get that? 5 and -1. Yeah. Just eigenvalues. Let me see if there is another function. Oh. Okay, ignore the eigenvectors for now. Let's focus just on the eigenvalues. So as you can see, it's relatively straightforward to calculate eigenvectors and eigenvalues. It's a little time consuming to explain why you're not seeing the same eigenvectors that we calculated. Our eigenvectors were 1, 2 and 1, -1. You're not necessarily seeing exactly the same eigenvectors. You're seeing something slightly different. It's actually very close. If you see, this is -1, this is +1, right? If I divide this by the same number, this is -1, 1. This is 1. This is 2 times that, 1, 2. Why you get these values is a little bit more harder to explain because but it's really exactly the same thing. If you notice, if I divide this by the first value, and then I divide oh, did I do it wrong there? Let's see, I was supposed to do 0, 0. I did that right. I did some indexing wrong. Can you help me spot what indexing did I do wrong? Let's see, did I do wrong? 0, 0 with 0, 0. That's fine. And 1, 1 with 0, 1. That's also fine. Oh, I should order mistake. I should first divide by this and then divide by this. So now these are the same eigenvectors we got, right? 1, -1 and 1, 2. Okay, so as you can see, this is really the straightforward way of calculating eigenvectors and eigenvalues. It's just a single line command, all the stuff that we did in today's class. So the intuition part, eigenvectors represent vectors whose direction does not change, but the length may change. And calculating that programmatically is simply create an array and use this method in using NumPy, linear algebra module, eigen function. For those of you who want the code, here. Oh, I can send the link also. Let's see. Okay. So is the programming part of it is just relatively extremely straightforward. So in the next 15 minutes or so, since we only have 15 more minutes, I want to introduce you guys to this one practical application of eigenvalues and eigenvectors. There are lots of other applications. The most popular application of that's probably more of linear algebra. The most popular application that I can at least think of eigenvalues is in face recognition. If some of you use some of you probably use Facebook, right? I don't know if there are any other tools these days with eigenvalues are the scale values. So this particular vector 1 minus 1 got scaled minus 1 times, so its direction got flipped. This vector 1 2 got scaled 5 times, so it increased by 5 times. So first eigenvalue corresponds to first eigenvector, which is these two guys. Second eigenvalue corresponds to second eigenvector, which is these two values here. Okay, so that's anyway. So one application that I would like to discuss of eigenvectors is in this thing called face recognition. I'll just see if so this is somebody's description of this face recognition. Can you see different faces on my screen here?
Yeah, we can see it.
Okay, so this method is called Eigenfaces. So if you notice, if you take different faces and take the average of their faces, it's this face. So this face represents the average of some 36,000 faces that this guy took and averaged out. What does average really mean? You add up all the values and divide by 36,000, right? Some of you already know what mean represents, right? So this is supposed to be the average face of these 36,000 faces. And this is supposed to be the difference from the average. If you notice, this guy has a very prominent forehead, whereas this guy's forehead is not that prominent, same as this one. Not that different from the, not different, prominent, but different. This guy's forehead is very different from the average forehead. This guy's forehead is very similar to average forehead, and this guy's forehead is extraordinarily similar to average forehead. But this person's nose is very different, nose is very different, nose is very different, nose is kind of different. Eyes are extremely close. So wherever you see more dark regions, that's where there is very little deviation. Where you see more grayish regions, that's where there is a lot of deviation. We'll go over this in the next session, but this is just an introduction to how we are going, what we are going to do. So continuing on, this part will explain, and then finally, these scary looking images are really how the first image that we were seeing is really being boiled down to this one tiny face. The second image is boiled down to this second face, and so on. So if you took different photos of this guy, the claim is all of them will look like this. And then you recognize this. So this method is called Eigenfaces. This is about a 30-year-old method right now, but this is one very interesting application of eigenvectors. Basically, this is called Eigenfaces. So instead of trying to recognize someone's face as a whole face, they are trying to find out the eigenvectors of the face. Is their nose pointed a little bit different than other noses? Are their eyes like bigger or smaller than others? So they are finding out all these different eigenvectors of a human face, and then trying to see when a new photograph is presented, they're trying to calculate the eigenvectors for that and see how close is this face to one of the other faces that we have already seen. So that's a cool application of this. It's something that has been done a long time ago. There are better methods these days than eigenfaces to recognize faces, but it's an old method and a very intuitively clear method. So your project actually involves building this eigenfaces and recognizing faces. Of course, I'll give you, so if someone's face has the same eigenvector as yours, then they can open your phone. Actually, it's so hard for someone's face to be exactly same in terms of eigenvectors. No. Homework is not facial recognition. That would be crazy difficult. Homework is to, so your twin can open your phone. Yeah, absolutely. Your twin can open your phone. But even twins have some small variations in faces. So it may or may not really open, because over time they may not have been exposed to the exact same conditions. Maybe one of them has like dark circles, other one doesn't have. One of them watches more plays more video games, and other plays less. So even twins may have differences in facial expressions or in their faces. Yeah, maybe one fell and got slightly fat. Yeah, so anything could have happened. One got fat, one got fit. Something else could have happened, right? So anyways, this is an interesting application. Hope you guys are excited about this. In this class, yeah, no skirt shrink. Yeah. A lot of things could happen on twins' faces, but that's not the focus of our class. It's really hard to do the face recognition part because a face is a big image. Instead of that, what we'll focus on is okay, instead of faces, we'll focus on numbers. Can you see my screen still?
Yeah, we can see it.
Right. So this is a 28 by 28 pixel image of the number 2, right? And this is just its eigenvectors. Because it's a 28 by 28 matrix, it will have 28 eigenvalues. If it's a 2 by 2 matrix, it will have 2 eigenvalues. If it's a 28 by 28 matrix, it will have 28 eigenvalues. If you can see these eigenvalues, notice that after I pass this eigenvalue, if you notice, this is exponential form, right? 8.08 times 10 power minus 1, 4.96 times 10 power minus 5. Look at these eigenvalues. This is minus 7 times 10 power minus 17. Compared to this eigenvalue is 10 power 16 times smaller, right? So the eigenvector corresponding to this is really, really insignificant. So this is why eigenvectors play a more prominent role. Instead of computing a 28-point vector, I can now simply cut off this eigenvector, let's say at this first 8 points, because every other point after that is so small compared to those first 8 points. Does it make sense? If you look at this value, this is 0.808. This value is 0.014. Right? So the first one is 0.808. The eighth value is 0.0145.
I
think your audio is
yeah.
messed up. Can you please reconnect?
Okay, let's try. Is it any better now?
No, Karthik.
Can you hear me now?
Yeah, this is better.
Oh, okay, cool. Okay. So the first eigenvector was 0.8. The eighth eigenvalue is 0.0145. The ninth one is 0.009. So as you can see, the values are dropping very quickly, right? This one is a work in progress. I'll send you guys, this has more homework for this class. Where are those first 8 points? You mean where are these first 8 points? These are the eigenvalues for this particular image. Oh, on the graph, they are not really, these are eigenvalues, right? Not eigenvectors. So if I want to draw them, I have to find out the corresponding eigenvectors. Let's see if I can print them easily. Yeah, it's really hard for you to see this. These are all imaginary eigenvectors. Yeah, it's hard to plot these in this shape. I would have to do some post processing on these. These are all imaginary eigenvectors, not really easy to draw them on two-dimensional plot, which involves just x's and y's. Yeah, but I'll give you something of a more starter code that you can use to draw these. Yeah, not this link. This is link I was using to experiment on something. I was doing some image recognition. So as you can see, this was supposed to be my test image 3, and I matched it to 3. So I was just trying out the code myself. So it works. In the next 4 weeks, you will slowly build towards it. Yeah, so I won't share the exact code with you guys because then you would not be doing it yourself. But that's the general idea. So the way we will do this general idea is by trying to find out these numbers. And these numbers are part of a very famous data set called MNIST digit recognition. Most of the people who do this, oh no, you don't have to memorize the functions. You don't have to start directly from here. I'll give you guys some starter code for this. So there are thousands of people who have attempted this on Kaggle. Most of them do it with neural networks, but we are going to do it with this Eigenfaces approach. Or it's just a more easier one. We will do it with neural networks in a few weeks from now also. So that's the goal. Just so you guys get familiar, the goal for this week's homework would be to read some numbers, because every image is just a bunch of numbers. If you notice here, I have these numbers here. So we just find the eigenvectors and find distance from the mean between these numbers, not distance from the mean, right? You find the eigenvectors for a sample set of images. And then when you get a new image, you try to find out what is this image decomposition along that eigenvector direction. What is the component of each of this image on that eigenvector? And then whichever component has the largest size or norm, that's the face or the image that it's closest to. We'll go over these terms. It's not difficult. It's just a lot of words. So the goal for this week's homework, I'll only take 5 more minutes because it's already midnight for me anyways, I have to sleep. So if you notice here, this set of numbers is what represents the image 2. Hopefully you can see some numbers here, right? Right, so there are some numbers, some non-zero numbers and lots of zeros. Zeros represent this purplish background. Non-zeros are the yellowish layer. So the goal for this week's homework would be, and I'll give you like some data set, to read a file, read the set of numbers, convert them into a 28 by 28 matrix, and then display them. So I'll give you different numbers and you would have to display them. That's the goal. Then next week I'll send out maybe some more instructions on, in next class we'll discuss a little bit about what this covariance is, how to calculate these eigenvectors, why we are subtracting something and adding something and all that. Then your goal would be to take a larger number of images, calculate the eigenvectors and try to recognize the images when you get a newer image. That's the goal for next week. Okay, so that's pretty much it. If you guys don't have any other questions, have a good weekend. Thanks for attending.
Bye. Have a great weekend.
Bye.
Thank
you. Bye.
Thank you.
Don't forget to subscribe and like. If you have any questions, you can email info@agoramatrical.org or comment below and we'll reply back. Maybe. And if you want to see practice things or anything about us, you can visit our website, which is basically the end of the email, but without the info and the end. So bye!